Welcome to the Electrochemistry unit for Chemistry 2. We are going to start with Lesson 1, Part 1, Video 1. And this is an introduction to the galvanic cells and electrochemistry. So electrochemistry is the study of the interaction between chemical and electrical energy. So we are going to look at how we can take chemical energy and transform it into electrical energy and the reverse. So we're going to divide this up into two main sections, the first being galvanic cells and the second being electrolysis. So with the galvanic cell, this is a device in which chemical energy is converted into electrical energy. One such device, I'll give you an example, is a battery. So there's a chemical reaction in there that generates a flow of electrons. So because we just finished up redox reactions and we know that they have to deal with electrons, we're going to bring our knowledge of redox reactions into electrochemistry because they are going to be the type of reaction in which we can derive a flow of electrons from as something travels from one chemical to another. So with that, all galvanic cells are going to have different parts. And those are listed down here: an anode, a cathode, a wire, and a salt bridge. So we're going to go ahead and define what these are. And an anode is going to be some type of electrode. And that electrode can be a metal, like copper, or it could be a neutral electrode, like graphite, which is sometimes used, plus a corresponding salt solution, which sometimes is referred to as an electrolyte. So this corresponding salt solution, what we mean by corresponding is the salt contains the same metal ion as the electrode. So it could be copper in a copper 2 sulfate solution. It could be iron in an iron 3 chloride solution. So as long as the electrode, if it's a metal, is made out and the salt solution has the same metal ion in it, it is going to work. Now at the anode, electrons are lost. So if we remember back to our redox, if electrons are lost, that is the definition of oxidation. And this is where we have the reducing agent. So at the anode, electrons are lost. So what happens here is the mass of the electrode decreases. So it goes down as solid metal becomes ions in the solution. So if we were to take the mass of an electrode, the metal, before and after running a galvanic cell, we would see that the mass goes down over time. Now, opposite of this is the cathode. This is the electrode plus a corresponding salt solution, which again would be an electrolyte, but it has to be different from the anode. So if this is a copper with a copper salt, this could be iron and an iron salt. So they have to be two different substances with two different metal ions. Here, electrons are gained. So this is where we have reduction. and the cathode is the oxidizing agent. And the mass of the electrode increases as metal ions become solid metal. So those are the two major parts. And there's a little mnemonic that can be used to help remember this. Red cat. So reduction happens at the cathode. So if you just picture a red cat, then that might be able to help you that, okay, reduction happens at the cathode, which means oxidation happens at the anode. So in order to get a flow of electrons, so if electrons are lost here and they're gained, we're actually going to have a flow of electrons from the anode to the cathode. And this is accomplished through a wire. And a wire connects the two electrodes and allows electrons to flow from anode to cathode. But we haven't created a full circuit yet. There has to be something else that connects the two solutions, and that is going to be a salt bridge. And a salt bridge is going to be something that completes the circuit. And allows, excuse me, and it's a tube of salt or like a slurry. It could be moistened paper, and it would have like an ionic compound on it in solution. And this allows charge distribution. So it allows ions to flow because we're pulling electrons from one side of this unit to another. One side would become really highly negative, one side would become positive. This helps balance the electrical charge in this circuit. So what we're going to be doing is measuring something called cell potential. And this is symbolized E with a sub of cell. And this is a measure, I guess you want to see that on the screen, a measure of the pulling force of electrons. And if you remember, if something has to gain electrons and something's losing them, it has to be pulled from one side to the other. So this actually measures this. And the units are volts, named after Alessandro Volta, who was a key player in electrochemistry. So volts have a symbol of V. And we are going to be looking at a standardized reduction potential. And the one chart that I ask you to print out or to have open is going to be a list of standard reduction potentials. So they're only in one direction, the reducing direction. So this is symbolized with a little prime symbol that tells us that it's standard. If you think back to electrochemistry, and we had standard conditions in which we measured our thermochemical values like enthalpy and entropy and Gibbs free energy, this is the same sort of thing. This is going to be based, we have to have a standard to measure it on, based on the SHE, the SHE, which is the standard hydrogen electrode. And it's given a value of 0.000 volts. So what these standard conditions are, all solutions are 1.00 molar. All gases, if they're measured, are at 1.00 atmospheres. And our temperature is 298 Kelvin, which is room temperature, just like when we talked about thermochemistry. So our next video, we're going to look at a diagram of what a cell would look like. And then in our third, we're going to look at how we use standard reduction potentials in order to calculate different things.